Okay, so what we are going to do now, first of all, any questions for the 1D problem? Any questions for the 1D problem? Any questions for the 1D problem here, what I've explained right now? Okay, if you don't have any questions, let's do it for the 2D problem. The 2D problem looked like this, right? Equals a times x, starting at x is equal to x0 at t is equal to 0. By the way, I get very good questions during the break, and very fundamental questions. Please ask those questions yourselves, your friends, discuss among each other, and if you can find a good answer, ask me. Some of the questions might sound very easy and very straightforward, too simple because you are too grown up. You are not too grown up. You are still a student. Okay? So ask these questions. A good question was, for example, if I'm at the equilibrium point, the derivatives are equal to 0. If I go a little bit away from the equilibrium point, the derivatives are not 0 anymore, but they're close to 0. Is it still an equilibrium point? It's not. Equilibrium point is a point. One point. And theta 1 is equal to 0, theta 2 is equal to 0. It's one single point, and that's the only point where you are at the equilibrium. If you move away from it, even the slightest bit, you will start moving, because theta 1 and theta 2 are not equal to 0. Okay? So how far do you need to move in order to check if it's coming back? Well, if it's a nonlinear system, you are talking of a small area, or some area. But if it's a linear system, you can move away as much as you want. It will come back because it's a linear system. The whole thing is linear. That's the beauty of it. Okay? Anyway, so this was my problem. In fact, we had this one. The one theta 2. Let's make it an example. And let's say we want theta 1 is equal to C1 at t is equal to 0. And theta 2 is equal to C2 at t is equal to 0. Now the question is, can we find theta 1 and theta 2 as a function of time? So here's what I'm going to do. I'm going to assume a solution and see if it will work. Okay? Assume a solution and see if it will work. So some lambda t times y and some e lambda t times z. So y, z, and lambda are constants. Constant real numbers. Not real. They are just constant. They can be actually more than just real. They can be complex, so they are just numbers. Is that okay? Don't do that. She has a special case. That's why she's coming late. But it's not an example for you. All right? So y, z, and lambda are constants. So this is the solution I assume, and we are going to see if it works. Okay? The way we are going to put this here is we're going to put this into this equation, see if it works. Of course, I chose them because I know the solution, but I'm just trying to show you something, right? Okay, so let's assume these things and put them into these equations. So first one, theta 1 dot will be the derivative of this thing. So the derivative of that will be lambda e to the power lambda t times y, right? This is the derivative of theta 1 is equal to, now this part here, right, is equal to theta 2. What is theta 2? Is equal to e to the power lambda t z, right? This is the first equation. Okay? This one here is theta 2. Theta 2, the first equation. Theta 1 dot is the derivative of this one. So let's do the second one. Theta 2 dot is the derivative of this thing. It's basically lambda E lambda T Z is equal to, now this one here, minus 2 times theta 1, it's this one, e to the power lambda T Y minus 3 times e to the power lambda T Z. Okay, 2 equations. All right, let's see what we are getting here. You can just remove these things from these equations, and you will get the following. Lambda Y is equal to Z. Lambda Z is equal to 2Y minus 3Z. Okay, so I'm trying to find, if I find solutions for these 3 unknowns, then I actually have a solution. How many equations do I have? 2. How many unknowns do I have? 3. Can I find a solution? Don't say. Can I find a solution? Doesn't look like it, but let's see. Maybe there's some magic here. So, lambda, let's write this in matrix form. I'm writing this in matrix form. Lambda YZ is equal to 0, 1, minus 2, minus 3, times Y and Z. Okay, written in matrix form. Take a look at this one. This is the same matrix as that one. And we call this matrix A, remember? It is the same matrix. So this is our matrix A. And it will always be the same matrix because of this relation here. If you call this now some vector x, what you will find is lambda x is equal to A times x. Does this look familiar? In fact, it will look like this. Maybe now it looks a bit more familiar. Does this look familiar? What is this equation? It's the eigenvalue problem. It's the eigenvalue problem. Is there a solution? If I give you A, can you find x and lambda? Can you find x and lambda? If I give you A, can you find solutions for x and lambda? Yes, it's the eigenvalue problem. So a minute ago we said we had 2 equations and 3 unknowns, but we cannot find a solution. Now when I write it like this, it looks like we can find a solution. So if I can find a solution for this, then I have a solution for my problem. Here. If I find lambda, if I find y and z, I have a solution for my problem, isn't it? So our problem to solve this turned into something quite interesting. It turned into the eigenvalue problem. And this is where someone said we can look at eigenvalues or something. This is where this is coming from. You can take a linear system, which is not one-dimensional, 2, 3, 5, 6-dimensional, whatever, and then try to solve it. You will see that the solution is actually hidden in the eigenvalue problem, where you're looking at the eigenvalue and the eigenvector of the matrix A. What is the matrix A? It is this one. You see? That's interesting, isn't it? So this is what we are going to do. So if I find the eigenvalue of the A matrix, I can find lambda. If I find the eigenvectors, I can find x's, and then I have a solution for this thing. And that will be my solution. Is that good? All right, so let's do it. So let's do it. Let's okay, first let's find the eigenvalues of the A matrix, of course. Right? We should find the eigenvalues of the A matrix. Eigenvalues of the A matrix. So how do I find the eigenvalues of the A matrix? I do this, right? 0 minus lambda, 1 minus 2 minus 3 minus lambda, and I look at the determinant of this and set it equal to 0, and that is my solution, right? And then I find the lambdas from this thing. Okay, so it will be minus lambda times minus 3 minus lambda plus 2 is equal to 0. You will have lambda square plus 3 lambda plus 2 is equal to 0. So lambda 1 will be equal to, what is it? Minus 2 and minus 1. So, two solutions. I don't even find one solution, but I have two solutions now. Okay, so what's next? I need to find x1 and x2. So could you please find x1 and x2? So what we're going to do next is, of course, we're going to take these numbers, right, and plug it into this thing and try to find x, right? So for lambda 1 is equal to minus 2, you should be able to find x1, the eigenvector. For lambda equals 2, you should find the eigenvector, let's call it x2. So could you please find them? So let's make it an exercise. Let's give it a minute. Please find the eigenvalues, eigenvectors. So I hope you found something like this. Okay, two eigenvalues, two eigenvectors. Do you find these things? I mean, it's basically here. You put the eigenvalue that you find for minus 2 You put it into this equation here, into this equation, and try to find y and z. And when you put it into that equation, you get this one. This is here x, this is here the eigenvalue, this is lambda times x, a times x, right? And you have these equations, and you have two unknowns, and you can find this. But you will see that this is not one solution here. You see that it's not one solution. It has many solutions. You see that? So I chose just one of them. I chose just 1 and minus 2. In fact, you will see any multiple of this one will still be a solution. So in other words, 2 minus 4 would also be a solution, isn't it? Isn't it? Or something else, you know, any multiple. I don't know, 4 to minus 8 is still a solution. So you have a lot of solutions. So the eigenvector has a lot of solutions, it's not only one vector. So what you're seeing here, the eigenvector, is only giving you a direction. Okay, the eigenvector is only the direction. Anything in that direction is an eigenvector of this problem. So for instance, here for y and z, okay, z is minus 2 and y is equal to 1, right? So it's basically this line here. This is the eigenvector for lambda equals 2. For lambda equals minus 2, sorry, this is your eigenvector. So anything along this line will still be an eigenvector. So you could choose this one, it will be still an eigenvector. So the eigenvector only gives you a direction. The magnitude we really don't know. I mean, don't know is not a good word. Any magnitude is fine. It is still the eigenvector. Any solution is fine. Understand? Same thing with this one, 1 and minus 1. Goes in any direction. So, which one am I choosing then? Am I going to choose this one for the solution? Because I still need a solution for this one. And the solution, these lambdas, are the eigenvalues, and y and z is the eigenvector. But the y and z is not unique. It can be anything as long as it's in that direction. Okay? Y and z is the eigenvector. Lambda is the eigenvalue. So anything in the direction of the eigenvector is a solution for this one. But I need a unique solution for my problem. So how do I find the unique solution? Any one of these things is a solution. So how do I find this? For instance, let's start here. The first solution I found for my problem is, lambda 1 is equal to minus 1 and x1 is equal to 1 minus 1. That's the right solution, right? So theta 1 will be equal to Did you find this or not? Yes? Okay. So theta 1 will be equal to minus 1 e to the power minus t times 1, and theta 2 is equal to e to the power minus t. Now this is a plus, right? This is a plus and this is a minus. So this is the first solution I found, but 1 and minus 1 is something. And the second solution is lambda 2 is equal to, this is lambda 2, right? Totally confused here. Sorry. This is lambda 1, this is minus 2. And x1 is equal to 1 and minus 2. And therefore, theta 1 is equal to e to the power minus 2t. And theta 2 is equal to x2 e to the power minus 2t. So, 2 equations, 2 solutions. So which one is the solution? Is it both of them or is it one of them? Because I just found 2 solutions. Which one is it? Hmm? Okay. But there are two different equations here. Which one is my solution? Right? You see what I'm trying to say? I have two solutions now. This one and this one. The question is, which one is the solution? I'm just still trying to find the solution for theta 1 and theta 2. And this was the assumption, and it looks like both of them satisfy these equations. So which one is the solution? You must have learned this in differential equations. Remember you learned something like general solution, particular solution? Remember that? This is exactly what it is. The actual solution will be a linear combination of these two. That's what we call the general solution. So theta 1 of t is equal to c1 times e to the power minus 1 plus c2 times e to the power minus 2t. And theta 2t is equal to c1 times minus e to the power minus t plus c2 times minus 2 times e to the power minus 2t. So it is a linear combination, that's why we call this a linear combination, of the particular solutions of each of these eigenvalues. So this is what we call a general solution. This is a general solution. General solution. That will be the solution. Understand? So from each eigenvalue, you find a solution with an eigenvector that depends on the direction, of course, of the thing. But at the same time, the linear combination of these give you the general solution. So C1 and C2 are constants. And this is a linear combination. A linear combination is it's a number plus that thing, plus that solution. So that will be your solution. That will be your general solution. Okay? If you get confused with this part, you might want to go back to differential equations. Okay? If you have two eigenvalues, you get one solution here, but then the actual solution is a linear combination of these two. Okay? All right. So, what are we going to do next? We need to find C1 and C2, and then I'm done with the problem. That's all that's left. Find C1 and C2. How do I find C1 and C2 in this problem? The initial conditions, right? That's what we still need to satisfy initial conditions. Okay, so let's give some numeric examples. I think I have some numeric examples here. Let's assume some initial conditions. A numeric example. Numeric example. And you can try different things, of course. Numeric example. Let's say theta 1 starts at 0 and theta 2 starts at 0.1. So theta 1, this is theta 1 is equal to theta, if you recall, and theta 2 is equal to theta dot. So which means the problem, I'm starting a problem where the pendulum is here, but it has a certain velocity, some angular velocity. Theta dot is equal to 0.1 radians per second. Let's say radians per second, and let's say this is radians. Okay? So you are at this point. Is it an equilibrium point? We are here. Is that the equilibrium point? No, it's not. Because equilibrium points requires that theta 2 is also equal to 0. Right? But if I say theta 2 is 0.1, it is not in equilibrium. It actually has a velocity at this point. It's just passing through this point. It's not an equilibrium point. So if you take a picture of this, you might think it's in equilibrium. But it's not. It has a velocity. Therefore, it's not in equilibrium. It has a velocity. So which means it will move up and down, it will eventually come back here because of the friction that I put over here. So we know it's stable, but it is the initial point. So this is the initial condition. So this initial condition must satisfy this, right? So which means that t is equal to 0, this equation should give me that. Okay? All right, let's do it. Theta 1 must be equal to 0. 0 is equal to C1. I'm trying to find that. T is equal to 0. What will this one be? T is equal to 0. It will be 1. Okay, so that's gone. Plus C2, I'm trying to find. And this one will be, again, 1. Right? Good. Second one, 0.1 will be equal to C1 times, so it will be minus, plus minus 2C2. Okay? Two equations, two unknowns. I should be able to solve this. So I should get 0.1 is equal to 1, 1, minus 1, minus 2, C1, C2, and you should be able to find C1 and C2 from here. What is it? 0.1 and minus 0.1. Perfect. Perfect. Now I have finally my solution. What is it? It's theta 1 of t. After all this work, I have a solution for theta 1 and theta 2. So, solution theta 1, 0.1 times e to the power minus t minus 0.1 e to the power minus 2t is equal to minus 0.1 e to the power minus t plus 0.2 e to the power minus 2t. So that is finally my solution. If I start from this initial condition, as a function of time, this is what is going to happen. Now I can plot theta 1 versus time and theta 2 versus time. Isn't that great? Whew, that was difficult. So, where does theta 1 start? T is equal to 0, 0, 0, 1, 1, minus 1, minus 1, it will give you 0. So it will start from 0, that's good. 0, 2 will start from where? It will start from plus 0.1, that's good. And then what's going to happen? The whole thing will start moving as t goes by. This will also start moving, right? It will also start moving. This will start moving. I don't know what it is going to do, but it's going to start moving, so I can plot this. Question number 1. Will theta 1 or theta 2 grow to infinity? No. Right? It will not grow to infinity. Because as t goes to infinity, this will grow to 0. This will grow to 0 as t grows to infinity. This one will go to 0. This one will go to 0. Therefore, theta 1 and theta 2 will be equal to 0 as t grows to infinity. Is that good to say? So, as t goes to infinity, theta 1 of t will be equal to 0 and theta 2 of t will be equal to 0. Is that safe to say? Yes. Are these points the equilibrium points that I had at the beginning? Yes. So basically, as t goes to infinity, the thing is going back to its equilibrium point. That's the first conclusion, isn't it? So is that equilibrium point then a stable equilibrium point? Yes, because the linear system is going back to its equilibrium point if I start from somewhere else. Isn't it? And look at this. If the initial conditions were something else, if the initial conditions were something else, let's say 4 and 5, what would happen? The only thing that would change would be C1 and C2. In other words, the only thing that would change would be these numbers in front of these exponentials. So it doesn't matter where you start, as long as you have minus t and minus 2t over here, you will always go back to 0 as t goes to infinity. Isn't that correct? So it doesn't matter what the initial conditions are. If you don't start at the equilibrium point, you will always go back to the equilibrium point as long as you have minuses on the exponentials. Isn't that correct? So what are these numbers, minus 1 and minus 2? Where do I get them from? They were the eigenvalues of what? Of the A matrix. What is the A matrix? It's this guy. Remember? This was the matrix that we obtained by linearizing the nonlinear equation around the equilibrium point. We got a matrix. You look at the eigenvalues of the matrix, and boom, they appear here. As long as they are all negative, this will go to 0. Isn't that correct? So I don't have to solve this problem all the time. I just need to look at the eigenvalues of that A matrix. If they are all negative, they will go back to 0. I mean, the states will go back to 0. If they are not negative, then they will grow. Let's say one of them is positive. Let's say one of the eigenvalues was plus 1, not minus 1, but plus 1. What would happen? You would have a plus over here, and this would grow to infinity. Right? It doesn't matter if the second one goes to 0. This will dominate. It will go to infinity. So all of them must be equal to 0. Even if one of them is positive, even if one of the eigenvalues is positive, this equation will grow to infinity. So if you're looking for stability of that equilibrium point, you need negative eigenvalues of this A matrix, and all of the eigenvalues must be negative, not only 1, not only 2, all of them. Even if one of them is positive, in the equation it will grow to infinity. Because this will go to 0 and the other one will grow to infinity, so theta 1 and theta 2 will blow up, basically go to infinity. Does that make sense? So which means the eigenvalues of the A matrix must all be positive. Negative. If they are positive, they will grow to infinity. Does that make sense? Yes, sir.
What if we have like 0.1 e to the power t and minus 0.1 e to the power minus t? That's why that time it will be.
Say again?
Two positive?
Yes. You mean eigenvalues?
Okay, it doesn't work. Okay.
Yeah. One of them will go, as time goes by, the negative ones will go to 0, the positive ones will go to infinity, if you wait long enough, right? As t goes to infinity. So that means all eigenvalues must be positive, negative for stability. You understand that? Okay. So then we are in a very good shape. All I need to look is at the eigenvalues. Few more things. Let's say the eigenvalue is a complex number, a plus bi. What happens then? Then one of them will start oscillating, right? This one will start oscillating. And if a, the complex part, is a negative number, yeah, okay, a is the real part, sure. A is the real part. If A is a negative number, this E will oscillate but go to 0. If A is a positive number, then this will oscillate but will grow to infinity. So it will still we will still be looking at the real part of the eigenvalue, because you understand that this is the eigenvalue, right? This was eigenvalue, I don't know, number 2 or something. Eigenvalue 2, and this is eigenvalue number 1, what did I say? Okay, this is 1 and this is eigenvalue 2, right? So if the eigenvalue was, it is -2 and -1 in this case, but if it was a complex eigenvalue, I would look at the real part of that, okay? So if I would plot the eigenvalues of this system in the complex plane, real versus imaginary, what do I have? I have -1 and -2. As long as the eigenvalues are on this side of the complex plane, my linear system will always converge to 0. Basically the equilibrium point of the linear system. Okay. Even if one of them is on this side, it will dominate everything else and the whole system will go to infinity. The linear system. Therefore, I need all of the eigenvalues on this side. Okay? What happens if you have eigenvalues that look like this? They are complex. Right? They are a complex conjugate always. Let's say they are a complex number. They have imaginary parts. They're plus minus this. What happens then? If everything is on this side, then it will still be stable, but it will be an oscillatory stability, which means the eigenvalue, the movement will look something like this, oscillation, but will die out. If you have a complex pair that is on this side, which is now unstable, right? It will make it oscillate and grow in large oscillations, basically grow to infinity. Is that good? Okay, so all I'm interested in, therefore, is what the eigenvalues are. Okay? One more thing, one more comment. You might want to write down these comments if you think they're interesting. I don't know. One more comment. Listen, we are almost done with this lecture. Now, listen. If the eigenvalues are bigger than some others, who will grow faster to infinity? This guy or this guy? Obviously -2. So the further the eigenvalues are on this side of the complex plane, the faster the system will go to infinity. I'm sorry? Yeah. It will. I'm sorry. The larger they are on this side, the faster they will converge to 0. That's correct. If it's a positive number, and it's a large positive number, it will diverge very fast. So it's not only positive, negative. It's also how big are the eigenvalues. If you have large eigenvalues, it means the system will either converge very quickly or diverge very quickly. If the eigenvalues are small numbers, they will converge slowly or diverge slowly. For instance, if you had eigenvalues that were very close to the origin, here. And then you have another eigenvalue that's very close to the origin. One is stable, one is unstable, right? But they are very small. Let's say if they are very small, which means the divergence will also be very small, which means you would have a number here that is 0.00001. It will diverge. It is unstable. But the divergence will be slow. If you have 10 million over here, what's going to happen? The divergence or the convergence will be very fast. So this is an unstable equilibrium point because of this root here, okay, which is on this side. But if it's very small, let's say it's plus 0.0000001, very small, the divergence will be very small. You can see it in these equations. So from a practical point of view, there's not much difference between this one and this one, although one is a stable equilibrium point, the other one is an unstable equilibrium point. One is diverging very slowly, the other one is converging very slowly. Basically, the system is not moving much. What happens if you have the eigenvalues here on the imaginary part? Which means that you will have only this B over here, no A, which means you will have pure oscillation, just oscillate forever, not go to infinity, not go to converge. So you will have that. So just by looking at the eigenvalues of the A matrix, we can tell a lot of things about this system. You see? And the story with this, looking at the eigenvalues and plotting on the imaginary real parts of the complex plane, does this remind you of another picture you saw in system dynamics? Yeah, of course. It is a characteristic equation of the Laplace transform, isn't it? You take the Laplace transform, find the transfer function, look at the characteristic equation, find the roots of the characteristic equation, and you have the same conclusion. The conclusion is that everything has to be on this side, isn't it? Okay. Now guess what? The eigenvalues that we found are the roots that you would have found if you would do the Laplace transform and look at the characteristic equation. If we do the Laplace transform, look at the characteristic equation and find the roots of the characteristic equation, they would be the same numbers as the eigenvalues of the A matrix that we found over here. Understand? I like this approach a little better because I can physically see what is happening to my states. This solution, the way you solve this, because it's a linear system, will be exactly the same for every linear system solution. So even if the system was 10 by 10, now here it's 2 by 2, even if it was 10 by 10, what would you have? You would have 10 eigenvalues, if it's a good matrix, of course. And then you would have 10 eigenvalues and therefore 10 particular solutions, and the general solution will be a linear combination of these 10. And even if one of those eigenvalues is a positive number, everything else will go to 0, but this one single guy will go to infinity and it will blow up everything. Okay? So the beauty of this approach is that once you have the dynamic system, have the equilibrium points, linearize it around the equilibrium points, you find the A matrix, look at the eigenvalues, and you can tell a lot of things about the equilibrium point just by looking at the eigenvalues of the A matrix. Because the eigenvalues of the A matrix are at the same time the roots of the characteristic equation of the transfer function. And that I'm going to show in the next hour that they are the same. In the next hour, we are going to solve the same problem using Laplace transform. Okay? So, 10 minutes break. Come back in exactly 10 minutes.